All right, welcome to The Explainer. Today, we are going to unpack a truly elegant trick in physics. It's a mathematical tool that builds this amazing bridge between the super chaotic microscopic world of particles and, the world we can actually see and measure. So let's just dive right in. Imagine you're trying to figure out the average energy of a gas in a box. I mean, you'd have to calculate the energy of every single particle in every single possible state it could be in, and then average all of that. It's an absolutely monumental, practically impossible task. Yeah, that direct approach, it's kind of like trying to cook a gourmet meal by deciding to grow the wheat, mill the flour, and source every single ingredient yourself from scratch. I mean, sure, it's possible, but it is so tedious. There has to be a better way, right? And of course there is. Physicists came up with this brilliant shortcut called the partition function. We just call it Z. You can think of it like a thermodynamic meal kit. It's got all the essential information you need, all bundled up into one neat, single function. And this is where the magic really happens. The process becomes incredibly simple. Once you have Z, you just do a few things. You take its natural log, then you differentiate it with respect to a variable we call beta, which is just related to the temperature, and finally, you multiply the whole thing by -1. And boom, just like that, you get the average energy. No insane summation required. And this formula right here, it just perfectly illustrates the power of the partition function. This one clean, simple derivative replaces a massive brute force calculation. It's an incredible piece of mathematical elegance that saves a, frankly, unbelievable amount of work. But, getting the average is really only half the battle. An average is just one number. Does that single number really tell us the whole story about what's going on in the system? Well, no. The source material gives a perfect example of this. You could calculate the average energy and find it's, let's say, 3 electron volts. But if you could actually look at the individual particles, you might find that not a single one of them has that exact energy. They're all constantly fluctuating, kind of jiggling, all around that average value. So what we need is a way to measure this jiggle. And in statistics, that concept is called variance, or fluctuation. It tells us more than just the average. It tells us how spread out all those different energies really are. So, okay, how do we calculate this variance? Do we have to go all the way back to that awful, painstaking method of summing up every single state again? Is our amazing shortcut at a dead end? Well, amazingly, the answer is no. We can go right back to our partition function. It turns out our little thermodynamic meal kit has another secret hidden inside. What if we apply that same differentiation trick not just once, but twice? Okay, so when you actually do the math, taking the second derivative of the natural log of z, you get this expression on the right. It's the average of the energy squared minus the square of the average energy. Now take a close look at that formula. Does that look familiar? It should. That is the exact mathematical definition of variance we just saw. This is just incredible. You differentiate the magic function once, you get the average. You differentiate it twice, and you get the fluctuation around that average. I mean, this is already mind-blowing stuff. Our one little function z gives us both the average energy and how much it jiggles. But this isn't just some cool math trick. This is where the physics gets truly beautiful, because this connects back to things we can actually go out and measure. Let's talk about something you can measure in a real lab with real equipment. It's called heat capacity. It's a totally fundamental property of a substance that just tells you how much its temperature is going to change when you pump in a certain amount of energy. So think about what we have. On one hand, we've got this abstract, purely mathematical calculation for the microscopic energy jiggles of particles. And on the other hand, we have this concrete, physical property of an entire object that you can literally hold in your hand. And here it is, the grand revelation. It turns out they are directly connected. The amount of microscopic energy jiggle happening inside a system is directly proportional to its macroscopic, measurable heat capacity. This stunning connection is a famous result in physics called the fluctuation-dissipation theorem, and it's a huge cornerstone of statistical mechanics. What it means is that the internal, unseen jiggling of all those tiny particles directly dictates how the entire system responds when you try to heat it up. A purely statistical calculation actually predicts a real-world measurement. And that is just the most profound takeaway here, this deep, elegant link between two worlds that seem so different. The quiet, internal jiggling of a system is directly tied to how it reacts to the outside world. And it was all uncovered through the power of one remarkable function. It really makes you wonder, doesn't it? What other deep secrets of the universe are just hidden away inside these clever mathematical shortcuts, just waiting for us to find them?